Car motion number 2. A car moves along a straight line. Its position as a function of time is given by the following formula, right over here. And we want to find its initial position, velocity, and acceleration. Then we want to know what time will it come to rest. Then how long after starting does it take the car to pass the x equals 0 point. What time is the car located at 4 meters. And then sketch the following graphs. And present all numerical answers with 2 significant figures. Part A. Find the car's initial position, velocity, and acceleration. There are actually 2 ways to solve the problem. You can just go ahead and take the first derivative with respect to time, and that will find the velocity, like was done here. And then take the second derivative of position, or the first derivative of velocity, and find the acceleration. And then substitute in t equals 0 seconds because we want the initial values. We'll do that first, but while you're doing it, think of a more clever way to do it by really examining this equation up here and relate it to a more general equation. So here's our derivatives. Well, there's x, here's the first derivative, second derivative. And we just go ahead and plug in the values of t equals 0, and initial position will be 5 meters. The velocity will be 2 meters per second. The car's barely crawling because 1 meter per second is 2.2 miles an hour, so it's going a little over 4 miles an hour. And its acceleration is negative 1.2 meters per second squared. So clearly this car was accelerating in the negative direction when we started the problem. Here's the more clever way to solve the problem, and it involves the second kinematics equation, which is right here. Let's compare that to our problem here, our car problem. And what do you notice about this? x0, the initial position, matches up with the 5. v0, the initial velocity, matches up with that 2. And then the only trick here is 1/2 times the acceleration matches up with 0.6. So by inspection, we get the initial position is 5 meters, the initial velocity is 2 meters per second, and then here's the thing, don't forget that half when you find the acceleration. You have 1/2 a is minus 0.6, and there's our acceleration, which exactly matches what we found on the previous slide. At what time will the car come to rest? We take our velocity equation that we've already derived, and that's 2 minus 1.2t, and just set it equal to 0 and solve for time. And we find that at 1.7 seconds, this car is coming to rest again. How long after starting does it take the car to pass the x equals 0 point? Well, you just set the position equation equal to 0, and that's right here. And then you can either go ahead and just plug that into your calculator and do the solve function, or let's try and do something manually here. It's hard to see if we can factor that. So let's get rid of the decimal, and we're going to multiply everything by 10 and see what we get. Well, that gives us 6t squared minus 20t minus 50, and we can actually factor that. So that's 3t plus 5, 2t minus 10 equals 0. That gives us 2 solutions. One is a negative solution, and one is positive. We're going to take the positive route. Sometimes, math gives us extra solutions that may not be applicable to the physical situation. In this case, if we had the car moving backwards in time by 5/3 of a second, the car would pass the x equals 0 point. But that's not physically possible, yet. At what time is the car located at x equals 4 meters? We will set the position equation equal to 4, and then we have this. And once again, we'll try the trick of multiplying it by 10, but in this case it can't be factored. So we need to use the quadratic equation, which is shown here, or you can use the solve function capability of your calculator. You're actually allowed to use that on the AP exam. So we plug it in, and we get negative 1/2 second and 3.8 seconds. And the correct physical solution will be the positive value, 3.8 seconds. Sketch the following graphs: position, velocity, and acceleration. Here are the graphs. And the easiest way to do this is to use the graphing function on your calculator, which is actually allowed on the AP exam. If you would rather do it yourself, then let's look at them. The acceleration is easy, it's a constant. The velocity is easy, it's a straight line. Position is the only tricky one, but one thing you know, somewhere there has to be a parabolic shape because of the t-squared. Now would also be a good time to go to College Board website where they give the definition of what they mean by sketch. You don't have to plot points, they're not totally interested in numbers, you just have to show the shape of the curve, asymptotes, where it crosses the x and y axis. They really don't get specific about do you have to label where it crosses on the x and y axis, but if you can do that, that would be a good idea just to make sure you get full credit. And of course, label your axes and put units down. Let's continue talking about the position graph. From part B of this problem, you know that the velocity at 1.7 seconds is 0. That's also where the slope of the position graph will change from positive to negative at t equals 1.7 seconds. You also know from part C that x is equal to 0 at t equals 5 seconds, so we can use that when we sketch the curve. The position graph, and you can see we've graphed it with a very nice software. It's openly accessible to everybody. It's graph-free.com. Graph-free is all one word. But let's see if we were sketching it how we would have done it. We know that the initial position is 5 meters. We know from our problem solving that at t equals 1.7 seconds, the slope changes from positive to negative. So that means it's concave down right at that point, 1.7 seconds. And the reason we know it's got a concavity is this t-squared here. And then it just falls off, and we know that the curve crosses the time axis at t equals 5 seconds. So there we go. And then of course we keep going to a negative position as time marches on. We don't need a lot of discussion on this one, right? This is just a linear graph, 2 minus 1.2t, y-intercept of 2, slope of negative 1.2. And we also, just to help draw it, we know that the velocity at t equals 1.7 seconds is 0 meters per second. So that's where we cross the x-axis. And the easiest graph, the acceleration is negative 1.2 t, just negative 1.2, so it's a constant line. The only thing you have to be careful here is if you're sketching it, you've got the axis here. What if this line was exactly on one of these axis points? Well, you'll want to draw it on your exam very thick. And a good idea would maybe draw an arrow there and just say a is equal to negative 1.2 meters per second squared, just so the grader knows that you drew the acceleration incorrectly.